So our final lesson on electrostatics is going to be focused on capacitors. Electrical devices that we use a lot in circuits, but that we will find we can understand the entire operation of simply from what we've learned specifically in this unit. So what is a capacitor? We've talked about it in a little bit of detail, but this is a device that's used specifically to store electric charge and by proxy, therefore, to store electric potential energy. And it's usually constructed by basically putting two conductors near each other, but they cannot be touching. Now, how we've talked about that so far in classes, these are usually been like two conducting plates placed near each other but not touching. And this would be the basis of what is known as a parallel plate capacitor. Pretty straightforward. And now all of these here would actually be small parallel plate capacitors. They've just been coated in something so that they don't get messed up at all. But you can also have cylindrical capacitors, as we see here, where we have one conductor literally inside another conductor, and electrolytic capacitors, which you'll be using in circuits, operate more on this principle. But ultimately, we're going to really be focusing specifically on parallel plate, just because they are easier to analyze and they give us enough of the conceptual understanding, while the ideas carry over to other types of capacitors. Okay, so let's talk about this though. If I have a capacitor originally, there is no charges on it. It is just two, well, there's no excess charges on it. It's just two conducting plates. Well, how do we charge it and therefore start storing charges on these plates? Well, we need to connect both sides of the capacitor, so each respective plate, to some voltage source, like a battery. So this battery has some voltage, delta V, could be 9 volts, whatever. And it's going to basically start accumulating on each plate positive charges that are with the positive terminal of the battery and negative charges with the negative terminal of the battery. So I'm going to start getting negative charges accumulating here, and I'm going to start getting, let's use a different color, positive charges accumulating over here. So these electric field lines are actually accurate because they're going from the positive to the negative. And eventually, over time, once the capacitor is finished charging, the potential difference between the plates will match that of the battery. So if this is 9 volts here, it will also be 9 volts between the two plates of the capacitor. And so specifically, we've now accumulated some positive Q on this plate and some negative Q on that plate, positive and negative charges. Now the interesting thing though is once we've done this, okay, so ultimately let's talk for a second, why did this even occur? Well, when we do this, when I connect these two plates to this voltage source, well, the charges from one end of the battery are attracted to charges at the other end, and this is basically create a route for them to become closer together, because these capacitors are very, very small distance apart, the plates are at least, so the charges have traveled through the wires, or more accurately, electrons have left the positive plate, and electrons have joined the negative plate, because they're attracted, the negatives and positives are attracted to each other. But the thing is, though, is that these positives and these negatives are still attracted, and now there's an excess on each one. So I can literally remove these wires, disconnecting it from the battery, and the charges are just going to stay there, because there's nowhere for them to go. You know, I basically just came and snipped the wires. They didn't go anywhere in between. So now I've still got positive Q on this plate and negative Q on this plate, and I've effectively stored a charge within this capacitor, and I've therefore stored electric potential energy. So what can we use with this is, well, capacitors are particularly useful for quick bursts of energy. While batteries provide continuous sources of energy that can only provide so much at a time, capacitors are much, much better at providing a lot of energy at once, or creating a lot of charge movement at once. A good example would be like, if you can think of like camera flashes, that flash of light is a humongous burst of current, and that's usually the result of discharging a capacitor. So how do we discharge it? Well, I just want to connect these two ends of the capacitor so that the electrons will quickly flow to the other plate, and you put something in between that can use this quick current flow and therefore harness this energy. So an example would be like a light bulb, for instance. I put a light bulb here, I connect the two ends, and you're getting a quick burst of light energy coming from this light bulb. So we've created a conductive path between the two ends, and that will discharge the capacitor and cause there no longer to be excess charges here. It is once again discharged. Well, what determines how much charge is stored in a capacitor? There's really two important factors here that can all be combined in this really nice simple equation, which is that the charge on, now this is important, each plate of the capacitor in coulombs. So this Q here, if it's the positive Q, that is one plate, negative Q on the other plate. So make sure we know that that's a charge on a single plate, is equal to C times delta V, where delta V, first off, is the voltage that the capacitor is connected to. So this is the potential difference across the capacitor. So if I connect it to a 9-volt battery, this would become 9 volts. So a bigger voltage, a bigger potential difference between the two plates, more charge is stored. Makes a good bit of sense. But what is this capital C here? And it is not coulombs, unfortunately. It is something known as capacitance. And the capacitance ultimately is how the capacitor is designed. This number of capacitance is telling us how many coulombs can be stored per volt we put across the capacitor. Now this coulombs per volts has another unit name known as the farad, or farads for plural, which we abbreviate with a capital F. So let's talk about this idea of capacitance, which is with a capital C. So this is a measure of how well a capacitor stores charge, really based on its specific design. And there's a couple of things that go into that. First off, we have the geometry of the plates involved. So, for instance, if I look here, what this is telling me is that if I have bigger plates, so plates that are in a bigger cross-sectional area, well, that will be a bigger capacitance. And that makes sense because you could store more charges on the plates if they're bigger. So capacitance is directly proportional to the area of each plate in meters squared. And additionally, it is inversely proportional to the separation between the plates. If the plates are really, really close together, more charges will be attracted. If we separate them out more, well, fewer charges are going to be attracted because Coulomb's law, those charges are further apart, not going to feel as much of an electric force. And that little d is the distance separating the plates in meters. So A over D. But what also is important here is what exists between the plates of the capacitor. Now, we will always have, at the very least, a vacuum. So we have to put this number here, epsilon naught, which has been a long time since we've seen this. We learned this way back when with Coulomb's law, where we talked about 1 over 4 pi epsilon naught was Coulomb's constant K. That's where this number, it's the same number, comes from. And this is the vacuum permittivity of 8.85 times 10 to the minus 12 Coulomb squared over newtons times meters squared. What this is ultimately telling us is how much electric field can permeate the region between the plates if there's just a vacuum. We're always going to have that. You can also add something between the plates called a dielectric. And a dielectric is characterized by something known as a dielectric constant. We're going to learn more about what dielectrics are in a minute, but this is going to be some number greater than 1. And if you have a greater dielectric constant, you have a more successful dielectric, more charge can be stored, the capacitance will in fact go up for the capacitor. Now, quick note, if it's just a vacuum, we just say, now, this is specifically, this letter is actually not a lowercase k, it's actually a Greek kappa. It looks like a k, don't freak out if you just write k. But for a vacuum, this value is literally just 1. So if I have a vacuum, this becomes 1, I can just ignore it, so it'll be just epsilon naught A over D. Whereas if I have some other material between the plates, I would have to put some different number here to multiply into it. And this is specifically the capacitance of a parallel plate capacitor. If we were looking at something more complicated, we would have to look at a different equation. And this is in units of farads, named for Michael Faraday, a very important physicist we'll learn about later. And these units in farads, remember, are 1 coulomb per volt. So a farad is 1 C over V. So that tells us how many coulombs are stored per voltage across based on the type of capacitor we have. Now be careful, it's super annoying. We have capacitance in coulombs, C and C. We have farads and forces, F and F. You gotta be real careful what's a unit and what is a variable. So let's look at a real simple example. Let's say we have the spacing between the plates of a parallel plate capacitor that's specifically a 1.0 nanofarad capacitor is 7 millimeters. And if we attach this to a 1.5 volt battery, how much charge is stored on each plate? And 2, what is the surface area of each plate? Well, looking at part 1, we can remember that we have this equation of Q is equal to C delta V, and we have the capacitance in 1.0 narofarads. We have the voltage is 1.5 volts. So I'm just going to multiply those together. So 1 times 10 to the negative 9 farads times 1.5 volts tells us that each plate stores 1.5 times 10 to the negative 9 coulombs, or 1.5 nanocoulombs. One will be positive, one will be negative. Really, really quick, easy, simple. Additionally, if we look at the other one, we say that capacitance is equal to kappa epsilon naught A over D. Now, we haven't said there's anything located between the plates, so we're going to assume it's a vacuum. If there's not anything specified, we can just assume kappa is equal to 1. But we're looking for the cross-sectional area, or the surface area, so we're going to move this around a little bit, and we're going to get A is equal to C times D. I just multiply that across, divided by kappa times epsilon naught. And we stick in the numbers, where we have C is 1 times 10 to the negative 9 farads, D is 7 millimeters, which is 0.007 meters, kappa is just 1, and epsilon naught is 8.85 times 10 to the negative 12 farads per meter. And if we stick this in our calculator, we get 0.79 meters squared. So the area will be 0.79 meters squared, which is actually pretty substantial. We would never have a capacitor this big. And what this is actually telling us is that the spacing between these plates is actually too large. The spacing really is usually going to be fractions of a millimeter, not multiple millimeters. Well, let's say you wanted to know how strong the electric field is within a capacitor. Now, first off, quick note, we've already learned that the electric field between these plates will be uniform, meaning that the electric force any charged fields within the plates will also be uniform, but we still want to be able to calculate it. Now we have to make a couple of qualifiers here, which is one, this is going to be for a parallel plate capacitor again, and we're going to actually assume there's no dielectric, so there's nothing stuck between the plates. If you introduce a dielectric, the electric field gets a bit more complicated, so we're not going to worry about that. But we have this equation that we learned relating the electric field to a voltage, so the absolute value of the electric field is equal to the voltage between the plates divided by delta R, the separation between them. So I can actually go ahead and say this is delta V over D instead of delta R, where D is the separation between the plates. We've actually already done some exercises like this, but there's another equation that we can occasionally use. So let's go ahead and see how we could get that. So first off, let's multiply the top and the bottom by the capacitance. This is no different than, for instance, multiplying by 1. So we do that, I'm going to stick C in the top and the bottom. And specifically, I'm going to rearrange it a little bit, so I have C delta V on the top, and I'm going to specifically put 1 over C over here, and then D over here. And the reason I've done this is, first off, C delta V, we've already learned, is Q. And additionally, we just learned an equation for C, which C is kappa epsilon naught A over D. So I'm literally just going to inverse that. And so now I have, first off, Q over D, that's just this right side. And on the other side, I already said kappa, we're going to assume there's no dielectric, that goes away. So this is going to be D epsilon naught over A. We notice that D's cancel. And we get this equation, Q is over epsilon naught times A, and the absolute value of that. So we're going to occasionally see these two equations for the electric field within a capacitor that's parallel plate, no dielectric. We don't, I should quickly note, this equation here should be on your equation sheet. It's useful. You're going to want to use it sometimes, but, that's really all we need to worry about. So we've got two different equations for the electric field within the plates of a capacitor. So let's talk for a second about what a dielectric is. So dielectrics are insulators, and that's really key, that may be placed between the conductors of a capacitor that actually increases the amount of charge that the capacitor can store. Well, how exactly does this work? Well, let's say we've got a regular old capacitor here, so I've got one plate positively charged, one plate negatively charged. There's nothing in between, so we just have epsilon naught for the vacuum in between the two, and this is the electric field going from positive to negative. Pretty straightforward. We've seen many situations like this. There would be some edge effects here, but we're not worried about that right now. But let's go ahead and say that instead we stick some insulator in here. Who knows what it could be? Rubber, some piece of plastic, paper, whatever, that has some dielectric constant, kappa. So what this does, though, is that, remember, insulators can't have charges moving throughout them, but what's going to happen is I've got positives on this side and negatives on that side. So for the individual molecules in this insulator, the negative, the electrons, are going to be pulled to the left towards the positive plate, and the protons, or basically the lack of negatives, will be pulled to the right towards the negative plate. We basically are polarizing every single molecule in this insulator, causing the charges to separate a little bit within each individual molecule. Well, if we do that, what you'll notice is that we're actually going to get a bunch of negatives here on closer to the side and a bunch of positives here closer to that side. So ultimately what's happening is we're actually creating an accumulation of negative here and accumulation of positive there. And this is a much smaller distance than between the plates themselves. And so we're actually going to pull more charges to each individual respective plate. And in doing so, we've increased the charge on each plate and we've increased the electric field between the plates. And also increased the amount of energy that it can store. So, this is, now a couple things here. This kappa is known as a dielectric constant. It is unitless, much like, for instance, the coefficient of friction. So it's a unitless value that quantifies the capability of some substance to be permeated by this electric field. So if you have a higher kappa, you're going to have basically more charges being stored. And there's tables of these that you can go find. They're usually experimentally determined. A couple of values we want to make sure we know is that, remember, if it's a vacuum, kappa is just 1, and we can just ignore it. But let's say you had a capacitor that doesn't have anything between the plates, but you're not in a vacuum chamber. Well, luckily for us, the kappa of just air is practically 1, 1.0006, so we can just round that off to 1. So we really only need to pay attention to kappa when we're in a specific scenario, when we have something between the plates that is substantial and that is very, very clearly noted. Alright, the last real big concept we want to talk about is how much electric potential energy will be stored in a capacitor. And really, what this comes down to is how much work was required to charge the capacitor. When you're putting work into separating those charges between the positive and negative plates, well, that is going to be stored as electric potential energy. So let's look at a couple scenarios real fast. When we first start charging a capacitor, so this is initially, I've got 2 parallel plates here, and there are no excess charges on either one. So initially, we have no charge stored, and so there's no voltage between the plates. Well, if there's no voltage between the plates, well then I could say, well, wait a second, the work is equal to Q delta V, but the voltage is 0. It literally is going to take no work for me to put, like, for instance, a positive charge here and a negative charge here, because we're not having to fight anything. And if that's the case, initially, we could say this is the potential energy stored in the capacitor. It's going to be about 0. We haven't really created much, we've not really stored much energy yet. But over time, we're going to start putting more and more charges on this, more positive charges on the left plate, more negative charges on the right plate, and it's going to start becoming harder and harder and harder to put charges there because we're basically pushing charges towards other like charges. So at the very, very end, I now have some voltage difference, delta V, between the plates. So I have a positive V and a negative V. And so this is when it's really fully charged, or pretty close to it. We now have a much larger voltage, at least much larger than 0 that we had originally. So when I do work putting a positive and a negative charge here, well, that's going to be equal to Q times delta V for each one of these respectively. So initially, not having to do really any work at all, very little energy charge. At the end, having to do a lot more work, specifically about Q delta V. Well, how exactly can we quantify this? Because initially, we're not having to do any work, and later on, we're having to do quite a bit. Well, why don't we just say throughout the entire charging process, we just look at, okay, what is the average work being done? So I have this would be the work plus the initial work over 2. And this would really just be, so Q delta V, I made Q capital here, because this one is 0, and this is not just for a single charge, this is now for all of the charges to move. So capital Q delta V over 2, and this is going to tell me this is actually the average work I've done, because initially it was 0, at the end it was double this amount. So this should be the amount I have to do at every instance. And in fact, that is the case, that the amount of energy stored in a capacitor is just 1/2 Q delta V, where Q is the charge stored on each plate in coulombs, delta V is the voltage between the plates, and UC is the electric potential energy stored within the electric field of the capacitor in joules. Now this is one way you'll see the equation. We do see it in a couple other forms, which is first off, remembering that Q is C delta V, I can plug that in here, and I'm going to get 1/2 C times delta V squared. And additionally, another form would be that Delta V, I'm just rearranging this equation, is Q over C. So if I stick that into the top, I would get 1/2 Q squared over C. These are all exactly the same thing. These are just different ways of looking at this equation. Depending on if you have a Q, a delta V, or a C, you can figure out the others. But these are three different forms showing us the electric potential energy stored within a capacitor. So let's do one last practice problem to kind of wrap things up. So let's say we have a parallel plate capacitors connected to a 10-volt battery. It has plates of area 5 times 10 to the minus 5 meters squared and is separated by a 0.1 millimeter spacing filled with paper, which is noted here, has a dielectric constant kappa of 3.7. A, what is the charge on each plate of the capacitor? And B, what is the electric potential energy stored in the field of the capacitor? Feel free to pause this, go ahead and give it a try, come back, let's see how you did. Well, if we want to do the first question, what is the charge on each plate of the capacitor, we're going to want to use the equation Q is equal to C delta V. But there's a thing here. We have the voltage, which is 10 volts. We weren't given the capacitance. So we're going to have to solve for that capacitance. So since this is a parallel plate capacitor, we can use C is equal to kappa epsilon naught A over D. And we go ahead and stick our values. Kappa is 3.7. Epsilon naught is 8.85 times 10 to the minus 12. The area of each plate is 5 times 10 to the minus 5. And D, the separation, is 1 times 10 to the minus 4. Keeping in mind a millimeter would be 1 times 10 to the minus 3. So be very, very careful with the scientific notation there. We stick this in our calculator and we get 1.64 times 10 to the negative 11 farads. So that's the capacitance. Now I'm going to just stick that into my other equation with 10 volts. Multiply them together. And we get 1.64 times 10 to the negative 10 coulombs. Or specifically, you don't have to do this, that's about 0.164 nanocoulombs on each plate of the capacitor. Now, if we want to know how much electric potential energy was stored in the field of the capacitor, I already solved for the capacitance, 1.64 times 10 to the negative 11 farads, and the charge on each plate, 1.64 times 10 to the negative 10 coulombs, and the voltage, once again, is 10 volts. We can use any of these three equations, and we should get the same answer, either 1/2 Q delta V, 1/2 C times delta V squared, or 1/2 Q squared over C, or Q squared over 2C. So for the first one, I go ahead and just stick in my numbers, 1/2 the Q delta V, and I get 8.2 times 10 to the negative 10 joules. Okay, let's say I want to double check. I go ahead and do the second one, 1/2 times the capacitance times the voltage squared, get the same number. And then the last one, I do the charge squared over 2 times the capacitance, get the same number. It doesn't matter which one you use, you should always get the same value. So we get 8.2 times 10 to the negative 10 joules stored within the electric field of this capacitor. So what were the main takeaways on this final lesson in electrostatics? Well, one, can we describe how a capacitor is charged and discharged? We hook it up to a voltage source. Over time, charges start to accumulate until they match that voltage source. We can disconnect it. They're going to keep the charges. And then to discharge it, we have to connect the ends and allow the charges to flow. Can we calculate the capacitance of a capacitor using the equation we learned, and by proxy how much charge it will store, specifically for a parallel plate capacitor, remembering that Q is equal to C delta V. That's an equation we really want to make sure we have down. Can we determine the electric field within a capacitor within limited circumstances? So remember, there was no dielectrics, parallel plate capacitor, we learned a couple different equations for that. And can we calculate the amount of electric potential energy stored within the field of a capacitor? And there are multiple different ways to do that.